Welcome everyone to the Power of Power, Elevating Power Analysis as a Tool for Credible, Fundable, and Impactful Research. This is an event sponsored by the Royal Statistical Society Emerging Applications Section, which I'm a member of. And my name is Elizabeth Eisenhower. I'm a lead statistical associate at Westat, and I also am an adjunct instructor in statistics at Penn State University. And I'll apologize for being one more Elizabeth in this mix. We have several Elizabeths here today, but this lineup is really a great lineup of speakers. I'm very excited about it, and we will try to differentiate, as you can see in parentheses, between all of the Elizabeths. So I'm going to give a very quick 3-minute introduction to power and power analysis, just to make sure that we have all of our terminology. We're all on the same page about what these things mean. So if you simulate test statistics under the assumption that you have the null hypothesis is true, you have no effect for your program, for example, has no effect, then by some random chance, you will have some cases where you will still reject the null hypothesis, even though in actuality, you shouldn't have. So that's falsely rejecting the null hypothesis, the type 1 error. We're calling it alpha today, and the convention is usually 0.05, but it could be other values as well. In the second scenario, we make the assumption that the alternative hypothesis is true, so the effect is not 0. In this case, we just pick a value and simulate a bunch of test statistics, but by some chance, of course, we're still going to have some probability of making an error. That's a type 2 error, the probability of falsely failing to reject the null. And the convention is that oftentimes that's set at 0.2, not always. And the power is the opposite of that. So the probability of correctly rejecting the null hypothesis or claiming that there is a program impact when this is true, that we should have done that. So just one slide with a bunch of equations on it. Power analysis is solving some function of these 4 pieces: alpha, which is that type 1 error rate, power, sample size, and effect size. So for example, if you want to detect an effect size of delta equals 0.3, you know that you want 80% power, you're doing a two-tailed test, and you're setting your significance level alpha at 0.05. There's an equation that you can use here, and plugging in those values using your standard normal distribution, you end up with 175 per group. So you have your treatment and control groups, for example, would be 175 each at minimum in order to achieve these values for delta, power, and alpha. The alternative way that you can think about this is isolating the effect size by itself on one side of the equation. And so in that case, given your alpha, your beta, and a sample size, you can determine a minimum detectable effect size. So this example comes from Eric's book, which I highly recommend checking out if you're interested in reading more about this, and you can also ask him questions today. So I'll say that this webinar, I should have said this in the beginning, but this webinar is completely unrestricted, so just try to keep your mics off as much as you can, unless you want to say something. And we would like to hold questions to the end. So we'll move through each of the speakers' presentations, and then after Eric is done his discussion, then we'll have time for questions. So I think now Sandra Jo Wilson will take over and give her presentation. And she's a principal associate of social and economic policy at Apt Global. Go ahead, Sandra.
Okay, hi everybody. Thank you for joining us today. All right, I think I have taken control. I'm going to click forward once, and if it doesn't advance, say something. Great. Quickly acknowledge the funding support for the project, as well as my collaborators, one of whom, Eric, is our discussant today. Okay, so this project, we called it empirical benchmarks for study planning and effect size interpretation. And the idea behind the project was to use a large meta-analytic database of randomized trials conducted in school settings, focused on behavioral interventions for students that measured social and behavioral outcomes. And these outcomes include things like aggressive or disruptive behavior, interpersonal competencies, self-regulation, internalizing challenges like anxiety or depression. So we were focused on these kind of non-academic outcomes in this particular case. And the idea was to collect all of the effect sizes from all of these trials on all these different outcomes and use those to help us think about benchmarking or interpreting the magnitude of the effect sizes from future studies, kind of assess how big is big. I won't talk about that today. I'll focus on the other purpose of the project, which was to provide some tools for estimating effect sizes for power analysis when planning a new study, or if you have a minimum detectable effect size, kind of gauging how realistic that might be. Part of the project involved developing an app that contains all of the effect sizes that we collected. And that's the URL is there. And then the paper that accompanied this is also on the screen. Okay, so what is study planning or power analysis for study planning? As Liz E said, when you're doing a power analysis, there are several parameters that you need to think about. In our case, we were thinking about the effect size, and this meta-analysis used the standardized mean difference effect size in the form of Hedges G. And the idea behind all this is you kind of want to get a sense of how to right size your sample for the study you're planning. And if you underestimate that sample size, you're setting yourself up for insignificant or at best kind of ambiguous findings from the beginning. If you overestimate your sample size, you could find yourself in a situation of not pursuing a study of a promising intervention because the sample size you estimated is too big for the resources you have, say. So when you're doing these power analysis, where do you get appropriate estimates for effect sizes? Like, how do you estimate that number? And it's not uncommon to see people use Cohen's small, medium, and large thresholds. Eric will talk a little bit about this later. People also use estimates from prior pilot studies or similar studies, or you might use meta-analysis of similar interventions. So there's lots of sources for these kind of things, but the context in which effect sizes are derived or from which they're derived matters. It influences the size of the effect size that you get. So for example, in education literature, we see universal interventions that are delivered to all the students in a particular setting tend to have smaller effect sizes on behavioral outcomes than interventions that are focused on students who are already experiencing challenges with their behavior. We see differences in age. So effect sizes can be larger with younger samples in certain situations than older samples. So when you're thinking about how appropriate your minimum detectable effect size is, or if you're picking an effect size for power analysis, you have to think about the context of your study that you're planning. Both the intervention, the population, where it is, timing of the study, that sort of thing. So The idea for our project was to collect all these effect sizes from hundreds of trials, code up details about the interventions, populations, outcomes, timing of the studies that generated them, and then model the effect sizes with the coded study characteristics as moderators. And then these models can be used to predict estimated effect sizes for different configurations of study characteristics that can serve as inputs for power analysis or used to benchmark a minimum detectable effect size against the distribution of effect sizes in the database. Okay. So let's do a quick example. There's lots of different ways you can play around with this stuff, but this is just a quick illustration. So say we have a researcher who's designing an RCT to test the impact of a universal skill building intervention to reduce suspensions in a general population of elementary school students. And her power analysis suggests that the planned study has a minimum detectable effect size of 0.05 standard deviations. So is her study sufficiently powered? Well, we don't know. So this is a screenshot of the app that contains all of our models behind it. And we can enter into the app the outcome, school disciplinaries, and then, excuse me, and then our moderators, which are the skill building programs, general population of students or universal prevention, and the elementary school age group. And then we also entered our minimum detectable effect size of 0.05. Not to be confused with statistical significance of 0.05. It's probably not a great example there. So what we find when we plug all these numbers in is that our predicted effect size is 0.13, so our predicted average effect size. The standard error is 0.08. So if we conduct a confidence interval around that mean effect size, it ranges from negative 0.03 to 0.29. So our researcher notes that her minimum detectable effect size falls within that confidence interval. We can also use the standard deviation of the predicted effect sizes from the model, which is 0.26, to determine the range of expected effects for similar studies. That range is a lot bigger, negative 0.38 to 0.64. So that's a pretty large range. So although the minimum detectable effect size is within the confidence interval of the effect sizes in the database with similar features, about 40% of the relevant studies in the meta-analysis reported effect sizes smaller than that. And the range of expected effects is rather large. So then it's up to the researcher at this point to kind of think about whether that sample size that produced the 0.05 minimum detectable effect size is appropriate for the context. And it may be that you want to go for a slightly bigger sample size, given how broad the range of expected effects might be. Just, it's kind of processing and thinking about all the features there. Okay, so the database does contain a large number of effect sizes, but selecting more parameters in the contextualizer means a smaller number of studies with the exact configuration of characteristics gets smaller. And so there's a trade-off there between specificity and precision, depending on kind of what selections you make. The models give less than full accounting of the possible sources of variation. So you would want to use a range of estimates to kind of put some boundaries on your estimates, as well as use other resources when doing power analysis. But the basic premise here is that the size of an effect depends on the context. And so that could be the intervention, setting, context, participants. And the idea is to kind of use that information to think in more nuanced ways about how you might conduct a power analysis to get the right sample size for a study or planning. And that's it for me. So I will let Beth take over.
Great. Beth Tipton is a professor of statistics and data science and a faculty fellow in the Institute for Policy Research at Northwestern University. So Beth should be able to take over the slides. You click take control at the top. Oh, you have control, so you can just click next.
I did that. There we go. Okay. Hi, everyone. It's great to be here. I'm going to talk about subgroup and moderator effects, which are a slightly different beast, though completely related. So a lot of times when we're designing particularly randomized trials, we're asking questions about what works. And those questions are about the average treatment effect. So we're asking questions that are just straight up about the average. So I'm putting that as delta here about the hypothesis, if the underlying hypothesis is if delta equals 0 or not. And in doing so, we're choosing a sample size for our randomized study that is, I like to say, just barely big enough so that we have our 80% chance of rejecting the null if the true delta is bigger, at least as big as this minimum detectable effect size. And so I want to really emphasize here that our selection of the sample size is that it is just barely big enough for what we need to do, as Sandra is pointing out, that we don't want it to be too big or too small in this case. But then we often, once we do our trials, want to ask questions about for whom and under what conditions. Sometimes this is because we didn't find a statistically significant average treatment effect, which leads us down this path. Sometimes we did find a statistically significant average treatment effect, and we're just not satisfied. We have all of these other questions. We want to know not just only did it work on average, but we have all these mechanistic questions about how did it work, and does it work particularly for this group or for that group? And so we might typically see these in two kinds of questions. We have subgroup questions where we might ask, is the average treatment effect for what I'm going to call subgroup X non-zero? This is just any subgroup. And then we might ask a comparative question, which is the average treatment effect for this subgroup different than for that subgroup? And that could be a moderator question. That's a question that could be a continuous variable as well. Anything that is comparative and asking, is there variation in effects, treatment effects across in relation to some other variable that is observed? The difficulty is that typically we have not designed our studies for this. And so I'm going to talk about that and then think about what we could do if we did design our studies for this. So it's not hard to imagine why this becomes a problem when you start to think about subgroup average treatment effects. I'm going to talk about this as a simple case. Imagine we just have two subgroups. We have, I'm going to call them X and W. And so our total sample is just, divided across those two groups. And now I'm realizing that this is not the greatest notation because I'm using n's here up here, but then later on I've shifted over to a cluster randomized trial. So just get the basic idea that these are two subgroups, it's been divided across two subgroups, but I'm suddenly going to shift to j's as mattering. So I really apologize. So I'm using an example of a cluster randomized trial down here, in which case I have 40 clusters. Each cluster has 30 units in it. So maybe these clusters are schools in my sort of education world often, and these are students. And I think I have an ICC of 0.2 and then, a covariate explaining 70% of the variation, blah, 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 details in here. But if I did that and I had all 40 schools, I could say my minimum detectable effect size for all 40 schools would be 0.27. And that's a pretty big MDES, but it might be doable for some curricular interventions potentially. If I then want to look at a subgroup effect across schools, and that subgroup, those two subgroups are equally divided. So I have half of the schools are X and half of the schools are W, whatever that is, rural and urban, small and large, whatever that is. And I want to test, well, is the average treatment effect non-zero in each of those subgroups? My MDES shifts to 0.39 in each of those. So now they're actually, it's much bigger, like in order to know in each of those subgroups. And if they're uneven, because, I didn't design my study for this, I just did my study, and then afterwards I wanted to look, and I'm like, oh, I wonder if it's actually, did it work for rural schools? And I just want to open up my data set and test if it worked for rural schools. Well, it turns out only a quarter of my schools are rural schools, for example. My MDES for them is 0.59. So this is a huge effect, right? I didn't plan for it. I'm looking potentially to see if there's a statistically significant effect, but I've kind of stacked the deck against myself in this process, leading to what Sandra had pointed out might be an ambiguous result. Is it significant? If it's not significant, is it not significant because there isn't an effect, or because my MDES is huge? The story gets harder, actually, and even gets trickier once we get to moderator effects. And in my experience, people really like to test these moderator effects with treatment effects. They want to know, oh, I wonder if we can, is there treatment effect variation? And this is often something we do after the fact. So this is just asking if the treatment effect is different across two groups. And just as a reminder, when we're doing that, we're comparing treatment effect estimates across two groups. And that means we have estimates of two things, which means we have two unstable things that are being estimated. So our variance is getting even bigger because I have a variance. Both of the things I'm comparing are estimates. So I'm just showing you here, same conditions. I'm just comparing. Now I'm saying, well, I have two groups and I just want to compare, let's say, rural and urban schools. And I have half and half. The MDES for that comparison is 0.571. So I just want to pause and think about that. I'm saying that's the difference between the two treatment effects. So on average, maybe if we think about this, I just said the average effect across them would be I think the MDES was 0.27. So you're saying the average effect is 0.27, but the difference between them would be 0.57. Think about how big that difference is. You're essentially going to have one of them at 0 and one of them at this really huge effect in order for you to find this. If they're unbalanced, if you have a small group, let's say only 10 rural schools and 30 urban schools, for example, this difference has to be even bigger for you to have adequate power. I mean, for if you have 80% power, for you to find an effect. So this is like a sad story, I think. This is where I think as a statistician, you're just sort of telling people like, look, you're not going to find things. So I've been thinking a lot in my own work about this design for moderators, that if we wait until the end, we don't find things. That's sort of the end result is what I'm saying. We consistently are doing this thing where we design studies for the main effect, get barely a big enough sample, and then we want to know these moderators, and then they're underpowered, so we get all of these ambiguous results as a result. So my question, the kind of driving question in a lot of what I've been thinking about is, how would you design your studies differently if what we were thinking about and planning for was moderation or heterogeneity? And so one little thing that you can do here is, I like to think of it as like, if you want heterogeneity out, you have to have heterogeneity in. And by that, what I mean is you need to have, if you want to really be able to increase power for these tests, you can increase the amount of variation in the moderator itself as a way of improving that power. So one idea is a question you can ask yourself in designing a study is, how much variation is there in this moderator in the population? And can I kind of match that in my study? So this is a way of not ending up in this extremely imbalanced design. If I know that there's a lot of rural and urban schools, maybe I want to make sure I've included those. This is true also with continuous variables. I know from some work that I've done that our samples are often much more homogeneous than populations are. The other thing you can do is actually purposefully sample more and purposefully try to get more extreme variation in your sample in these moderators. And in doing so, you can actually, for a fixed sample size, improve your MDES. You can improve your power by increasing that variation. So just some concluding thoughts here. One is I just want to remind everyone that a study is not powered. A specific hypothesis test is powered. So even though you powered your study for, you got a sample size and you can say my study is adequately powered for the average treatment effect, that does not mean it's powered for these moderators or these subgroups. The second is that tests of subgroups and moderators are typically severely underpowered. And what that means is that we often have ambiguous results. And the third one is that we can't prove that there's no variation in treatment effects. And so this is really hard, even if that means that none of your moderator tests are significant. You're finding nothing is significant because we didn't plan for it. You're left in this perplexing situation of not being able to say, this is a constant treatment effect. You didn't actually design the study in any way that would allow you to say that. Finally, just to end, I like to say we can do better, that if we really care about treatment effect variation and we think that it matters, it just requires that we have better theories, that we stop thinking in silver bullet theorizing about interventions, and that we just carefully design our studies better, either individually or in a coordinated way. And I've just got some links here to a couple of papers that I have, and as well as a link to Nyambo Dong's power analysis software, which includes which is Power Up. It includes software for moderator analysis, power analysis. Thank you.
Thank you, Beth. And you can actually, as a participant, click on some of these links in these slides the way that we're presenting, which is kind of cool. So thank you so much for that. And we will move next to Liz Stewart. And so Liz Stewart can go ahead and take control. And she is a professor and chair in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Thank you.
Fantastic. Thanks. You see my title slide now? Great. Okay. Thanks so much for organizing this. I'm happy to be here. I'm going to add yet another set of complications to the sort of nice, easy power analysis sort of setup that the other Liz introduced at the beginning. And in particular, and by the way, I'm going to have I think 0 equations. This is mostly just very conceptual and will sort of expose you to some different concepts and, again, complications. And so really what I'm going to dig into is this scenario where we didn't randomize. So an implicit theme, sometimes implicit, sometimes explicit so far, has been a randomized design where we randomize people to 2 groups and then want to say the power to detect differences between those groups. But, oops, sorry, I guess I can't use that button. I have to use this one. So the challenge is that often, though, we don't randomize. So we are, in this, I think throughout this entire webinar, we are focused on this sort of interest in studying one exposure or treatment versus another. But again, in many contexts, we want to study things that can't be randomized. So instead, we're left with a non-experimental study. Non-experimental studies broadly are a whole range of methods and designs, some of them listed here: regression, discontinuity, difference in differences, etc. All of them are extra complex in terms of power. And, sort of in some ways, like the nice, easy formulas that were shown earlier just don't work in these other designs. For now, for today, in my 6 minutes, I'm going to focus on these comparison group design scenarios where, again, we sort of have 2 groups, treatment and control, but again, where they weren't randomly assigned. And we are trying to deal with observed confounding through methods like propensity scores. There are methods that exist for power for regression discontinuity, interpreted time series, etc. But they're not going to be my focus today. So I wanted to take a step back for a minute and say, why might we care about power in non-experimental studies? So you heard earlier from Sandra especially about why often in a randomized trial, we do a power analysis to figure out how many people should be enrolled in that study. How many people do we need to actually recruit? Typical non-experimental studies, though, are often using existing data. We don't have we're not trying to decide, should we survey 100 people or 1,000 people? We just have a data set in front of us. So, sort of mulling over why do we need power calculations in non-randomized settings? And I think there's, sort of 2.5 reasons. One is that sometimes, even though we're not doing formal recruitment, we might want to understand sort of in advance, is a study worth doing? Do we have any hope of sort of seeing what we think we are interested in? Is there any hope for power? Relatedly, basically every grant application I've ever written asks for a power calculation, even if actually I think it's not really informative or really going to change any behavior, but there's sort of that boilerplate, like you have to show it. The second scenario, which is a whole other can of worms that maybe we can come back to in the discussion, is one where sometimes, in my experience, actually the more relevant scenario is one where we find null effects and we sort of want to post hoc understand, like, was this a power issue or are these sort of real? Of course, as statisticians, I think we all realize post hoc power calculations are incredibly complicated and usually not valid. But that's often the scenario that we find ourselves in non-experimental studies. So on the right is a figure from a paper I was on, led by Beth McGinty, where these are the point estimates of estimated effects of a state policy on opioid prescribing. And you can see these are basically centered at 0 and with really very tight confidence intervals. So in this case, we didn't really, it was not like it was basically 0. It was very obviously 0. In some other cases, it might be harder to sort of disentangle, well, are the effects really 0 or was it partly limited power? So there are scenarios where I think we might care about power in non-randomized studies. But again, I wanted to just put out this idea that I think it's sometimes a different goal than in, say, a trial where we are explicitly going to recruit people or a certain number of people as a result. So let's say we do want to calculate power. Maybe we're in that sort of first scenario where we're trying to decide if some study is worth doing. And so we want to do some a priori power calculations. So those little formulas we saw earlier are only valid for randomized trials. And there's a whole long history of statistical work on this, going back to Bill Cochran and others in the sort of, probably 60s, that in fact, the power in non-randomized studies is going to be lower than the power of a comparable randomized trial, because because it has similarity between the treatment and control groups, that power is the highest to be able to detect a difference in outcomes. The fact that in a non-randomized study, the groups might be different on confounders means that the power itself is going to be lower. What is interesting, though, is there's been actually surprisingly little work on sort of formulas and methods to estimate power in these contexts. So there's been some work, and at the end, I have some links, and there are these 2 references here. So for example, Rubin and Thomas, 1996, showed some equations that showed sort of the amount of bias reduction that you could have in a non-randomized study. And they showed that that was a function of things like sample size, like in a trial, but also things like the number of covariates, the initial confounding, essentially the difference between the treatment and control groups on those covariates, the correlation between the covariates, the relationship between the covariates and the outcome. It is just a much more complicated equation in a non-experimental study. It's no longer sort of mostly just, a couple variances, a couple sample sizes. I do want to give a shout out and flag for a brand new paper from about January by Liu, Zhao, and Li, which gives, I think, one of the most thorough investigations of power in non-randomized comparison group designs, including some software. And they use a propensity score as a way to sort of make things tractable. And it is one of the sort of, finally, I feel like people are starting to use some of the old theory and connecting it to actual power calculations. Okay, but in my last 2 minutes, I also want to be a little provocative and say, is power what we actually should care about in a non-randomized study? So in randomized trials, sometimes the way I think about it is that in a trial, we kind of have the luxury to worry about power because we know we have an unbiased effect estimate, setting aside noncompliance, missing data, et cetera. In our sort of typical kind of easy, well-done randomized trial, we know we have an unbiased effect estimate. And so then we can say, all right, how do we get the most precise estimate of, or, sort of inference around that? The problem in non-randomized settings is that we don't have that bias guarantee. And in fact, bias and reducing confounding might be our primary concern. So there's actually this long history of work. Paul Rosenbaum is one of the people who's, I think, thought and written the most clearly about this, is that there are a lot of scenarios where we might actually, in non-randomized settings, where we might prefer a lower sample size and lower statistical power, but more similarity on observed and unobserved factors to make the groups, again, more similar to each other and reduce confounding and reduce bias. So now, again, in my last minute, want to just introduce this idea that in a non-experimental study, we might care more about this concept called design sensitivity. And this is a concept, and actually there's a quantitative metric for it developed by Paul Rosenbaum and colleagues, which basically captures how sensitive a study is to confounding. And he sort of talks through that, like in a non-randomized study, what makes it strong is not sort of necessarily just kind of sample size, but also things like the strategies that help us reduce sensitivity to an unobserved or an observed confounder. So here are just some examples. On the left is this really nice paper by Jose Zubizarreta and colleagues where they talk this through in a nice applied example. And then I've written a commentary with David Hanna, sort of pushing this and saying, like, maybe in these scenarios, we should care more about design sensitivity than statistical power. So I'll leave, I didn't put links. I didn't realize that nice, cool trick. But here is a slide with a few references, and I look forward to the discussion. Thanks so much.
Thank you, Liz. That's great. Now, I think our next speaker is our discussant, Eric Hedberg, and Eric is a lead experimental data scientist at State Farm. And Eric, I'll let you take it away.
Thank you. Thanks, Lizzie. Hi, guys. My name is Eric Hedberg, and I just want to sort of state for the record that I come to you as Citizen Hedberg, and so I'm not talking about stuff related to my work at State Farm or, having anything to do with that wonderful organization that I work for. So just getting that out of the way. So let me find the right button here. All right. So a lot of times when I used to sort of teach about this stuff, I used to sort of think about MDES values as sort of like an eye chart for your sample, because, even with hypothesis testing, we have like triple negatives and it's hard to kind of keep this straight. And so I have this idea of the eye chart that we used to use when we were kids, or I still use every time I go get my glasses. Really good samples can see very small letters. So really large samples can really sort of detect small effects. Not so great eyes like mine can only kind of see really big letters or sort of really big MDES values. And so I just kind of wanted to throw that out there. And our wonderful set of speakers really sort of talked a lot about all the complications that go into even thinking about MDES values, right? They vary by outcome, by the population, by age. There's, differences between sort of raw impacts and impacts for specific subgroups, and how you sort of power your studies and how much observations you need in your design really goes into your ability to detect those. And then, as Liz Stewart just talked about, the estimates are really tied to sort of the S-demand, and so a lot of times when you're not dealing with randomized trials and looking for average treatment effects, a lot of times you're looking for slightly different types of treatment effects. And then you also tend to assume that they're insensitive to these unobserved confounders. And so you have to think about that. So it's all really, really complicated, but power and MDES are all relative to the design you have and the population and what you're working for. And so, with apologies to David Mamet, I like to sort of think of this dumb little phrase ABCDE of always be critical of the detectable effects in your studies. right? To sort of, have this sort of image of a young Alec Baldwin in your head being mean to people. Always be critical of these MDESs and really sort of think through what you're putting to paper in your study designs or what others have put to paper as you are peer reviewing other study designs. The other thing I really want to sort of emphasize is this idea of PICO, of when you're planning your study, you want to be thinking very carefully about your population, your intervention, what you're comparing it to, what's your outcome. And that is really a lot of what's driving the sensitivity of your study. And it's not these sort of shirt-sized rules of small, medium, and large, which at best were a great description of 1970s psychology students. And so I would really like to just be bold here and really just sort of say, I would like to put away these shirt sizes and bury them and really sort of force people to really talk about what they're studying, who they're using for this study, and what these outcomes are. So, please stop using these shirt sizes. Just to put a finer point on some of this stuff, there's a lot of variation, and this really sort of matters. So if we think about education, and this is some earlier work I did long ago with the Helios Foundation, if we think of so we have a raw impact of 2 ACT points from an intervention. We do this intervention and we want kids to do better on these standardized tests. We have, we think it's going to get 2 points. Well, this 2 points translates to very different deltas based on the natural variation we have in different sort of subsets of the population. And so, again, I'm not going to belabor this, but, because the standard deviations for these different subgroups of Arizona students differ, really only one of them, if this was the actual effect that we observed, would have been statistically significant. So not only do I want to ditch shirt sizes, but I also want everyone to really think about what's the natural variation in the folks that you're studying. And so how does that play into it? And so you want to be very thoughtful about that. A lot of times when I, taught stats for undergrads, I talk about correlations and stuff, and I'd always get the question from the students, well, what's good? What's big? And this is, again, an issue that comes up over and over again. Sandra talked about this. This is just sort of an example of, from education, again, natural growth year over year. And so we find that, in reading scores, younger kids tend to just learn more in terms of their standard deviations than older kids. Part of this is due to just, kindergartners just learn a lot because they're starting, and 11th graders, as far as reading, we're pretty good at that. So they're not learning a whole lot. So part of that is sort of natural change. The other part of it is just sort of the heteroskedasticity that occurs over time. Most kindergartners come in not knowing a whole lot. By the time you get to 12th grade, you have the kids that have learned a whole lot. You have some kids who haven't learned much since kindergarten. So you just, the denominator of these effect sizes also changes. So there's a lot of moving parts to all of this. We've been talking a lot about sort of education outcomes, test scores, psychological scales, but, this also really matters for other types of outcomes. And in fact, I think there's some opportunity, and I don't think this has been studied as much, for benchmarking other types of outcomes. For example, criminal behavior, things that, like age crime curves. What's really nice with these sort of, exponential family type of outcomes, these sort of, counts, binary outcomes, is we have this nice attribute that, the variance is usually the function of the mean in this case, right? So that's really helpful to us. We don't necessarily need all this detailed individual level data to create these benchmarks. If you get yourself a good age crime curve, you kind of have a lot of the information you need to sort of figure out what's natural growth and, say, the chance of being arrested. For example, I took an age crime curve from a paper. I have the site below. I converted that rate into a log odds. I fit a quick polynomial, and you see the fit was pretty tight on that logit age crime curve. Once I had that algebraic expression, I could do a few things and say, well, what is sort of the year over year gains in the chance of being arrested in Cohen's D units? And that's sort of this last column on this table, where we sort of see for 12 to 14-year-olds, that sort of growth in deviance is about 0.17 standard deviations. And then, it goes down for the 15s. This probably would have been really great to have a sense of when they were doing this gang resistance evaluation, because they powered their study, probably based on Cohen's d. I don't know that for a case. And they were doing a cluster randomized study. And, back then, not everyone would pull an ICC and do the right power formula for that too. What they observed were sort of standard deviation effects of, about 0.1 or less. And when I kind of went through and said, well, that's kind of reasonable for what I'm looking at, right? If sort of the year-over-year gains for the same 13-year-olds are about 0.2 standard deviations, having an impact of 0.1, that seems in line. That makes sense. That's not an unreasonable, but they didn't power for that. And so they found nothing significant, or not, very, very little significant. So this is sort of a case of sort of like, boy, if they made a little age crime curve and sort of planned their study accordingly, maybe they would have found stuff. It could have been that this great program worked, frankly, great, but they didn't have the sample to detect it because they didn't have the information available to them to sort of figure out. And so with that, I sort of leave you with way more questions than answers, but I think we're all together as this panel really trying to say, power analysis is important, but power analysis is not just a checkbox. It's not just a shirt size. You really need to understand what you're working with and who you're working with to adequately power the hypotheses in your study. And so with that, I'm happy to open it up for discussion. People can type stuff in the chat. Elizabeth Eisenhower and I will moderate. Feel free to off mute, off camera if you just want to jump in. Liz Eisenhower?
Great, thank you. Does anyone have any questions? Yeah, you can feel free to, you can raise your hand, you can just go ahead and unmute.
I have a question, if nobody else does, but I want to give folks a second because I'm sure you're sick of listening to me. Okay, so this is a question for the whole group. So in a lot of fields, especially psychology, and it's also been found to happen in sort of medicine, we have what we call a sort of replication crisis, right? Replication crisis is sort of the Googleable term. And what this crisis is there's lots of landmark studies that found huge things and had a big influence on the field. And then when other people kind of go back and say, let's try to reproduce this, let's try to see if power poses actually do what people think they're going to do, say, not to pick on power poses, but came to mind. They were a large fraction find that things aren't replicated, right? And so there's a lot of reasons for this. One of the big reasons that a lot of people point to was sort of underpowered studies, in that if you have sort of this small sample, not only are you sort of underpowered to sort of detect sort of the main effect, but with a small sample comes a pretty big confidence interval, and you could win the lotto, right? There's, even with null effects, you still have a 5% chance of getting statistically significant at 0.05, right? And so that sort of becomes sort of this issue. And so my question is, and I sort of have a question for everyone here. So I'll ask Dr. Wilson and then Dr. Timpton, Dr. Stewart, you guys can answer in turn. So Dr. Wilson, in all your work with the Prevention Science Clearinghouse, what is sort of your impression of the state of the art in that field for sort of sample sizes and things in that area? And so I'll let you give an answer.
Okay, so the Prevention Services Clearinghouse is a large federal clearinghouse of interventions intended to prevent foster care placements. So the kinds of interventions in there would be parenting skills interventions, mental health programs for parents, because mental health is a risk factor for child maltreatment, substance use programs for adults, that sort of thing. My sense of, I don't know if we'd call it the replication issue in that context, but yes, I think we do see like later studies of the same intervention maybe don't look quite as exciting as the original studies of an intervention. In terms of power analysis, I've been kind of surprised digging into this literature how uncommon it is to have people report that. It's growing, I think, a little bit in the mental health area, maybe an influence from kind of the public health field. But we don't see it a lot. So it's hard to know if that was part of the planning of the study. You know, so I guess that's my answer. I think these kinds of questions that we're talking about today have not trickled down into this kind of child welfare research area just yet.
Well, hopefully soon. And, you know, I remember when I wrote my little power book, I had a bunch of academic buddies who'd say, well, you're going to get all these citations from this and stuff. And I really haven't. And I realized, oh, yeah, because anyone who cites this book is going to be in a grant app. And that usually doesn't get, you know, doesn't usually show up in Google Scholar. Dr. Tipton, so you and I sort of, as we grew up in this field, sort of grew up while education as a field had this sort of, you know, massive sort of increase in sensitivity power. So I have sort of since sort of left that field, but I just wanted to sort of get your impressions as sort of you think back on power in the education field.
Well, I was actually just thinking about this sort of power pose thing in the psych case, because I think it's actually a little instructive. The way that psych studies are able to be powered, you know, to have adequate power with big effects. So they're small studies. So think about, I mean, it's part of what I was going down in my head was thinking like, one of the problems I think that happens in psychology a lot, in social psychology, is that we make big deals out of small studies. So they find something in a small study and it makes the New York Times. And then they don't find something in the next small study, but they're small studies. And so one could say, well, are they adequately powered? Well, they would say that they are adequately powered, that they have a big effect. But how did they get the big effect? Well, why do they think that they're adequately powered for the big effect? Well, because what you do in order to get a big effect is you do everything you can to remove variation, right? That's the entire discipline of psychology. You make controlled experiments, and they're really good at this. It's really fascinating when you work with psychologists in labs at how good they are at making a comparison condition exactly the same, except for this one thing that they're changing, right? So that they're like only manipulating this one thing that they can know that that's the effect, but they're essentially removing variation. And they also do that by who they include in the trial, in the study. So they have inclusion criteria in various ways. So all of these are ways that allow them to be able to get huge effects, to say, I've designed my study for a delta of 0.4 or 0.5, and therefore I only need a small number of participants in order to do this study. They've done the power analysis. Yes, they have correctly done all of these things to do it. They also have highly aligned measures. They've done everything in this system. The question of replicability then becomes this question that's, I think, entwined with these questions of generalizability as a result. You know, once I move it to a new sample, once I move it to a slightly different measure, once I move it to less researcher control, does it hold? And so I think there's this trade-off in some ways. I think this moves beyond, I guess what I'm saying, moves beyond psych even. There is an inherent tension between, in RCTs also in general, between what improves power and what makes something more generalizable or useful. I see that in the broader education space too, that randomized trials that have great power, often the way we make them have more power is to make them more homogeneous in some way, more focused, more schools that are like each other, to have more similar comparison conditions. All of those are ways to, for a fixed sample, improve power, but that improves power at a cost to making it generalizable and potentially useful. So there's a tension, I think, between power and usefulness or generalizability that we often don't talk about. And I think that is connected to the replication in that because we've under-theorized these issues of who's in the sample. and under-theorized these questions of treatment effect variation. So we're surprised when the effects don't generalize. We're surprised when there's variation, or we can't explain it, or we can't make sense of it. And then when we don't find the same effect in another sample, we don't know why, because we didn't measure things. We just don't have a good sense of it. We didn't anticipate it in that way.
Yeah. Dr. Stewart, I'm asking you for your view from public health on all of these issues. And are eggs good or bad?
Are what, good or bad?
Are eggs good or bad? Because that
eggs-
always goes back and forth having to do with replication.
Got it. Oh, yeah. Yeah. I'm not going to wade into nutritional guidance. Yeah, it's interesting. There were two lenses I was going to take on this question. And one is that one of the tensions that I've seen, certainly in the education world as a straddle sort of worlds, also in mental health, is this idea of sort of the role of pilot studies. And actually I'm going to put a link in the chat. I wrote a paper years ago where we sort of showed the problems of exactly what you're talking about. But it is still the case that sometimes people will do, like in my NIH funding world, there's like R21s, which are sort of small pilot grants. And someone will do an R21, and there's still this misunderstanding about what the role of a pilot study should be. It really should be just about assessing feasibility of the design and the recruitment and sort of the measures and things like that. People, though, will still pull an effect size from a small pilot study and use that to power their subsequent study. And that, for the reasons you introduced this question with, can be completely misleading because those point estimates are so noisy. So we wrote a little paper in a little Shiny app it's a very basic point, but just to illustrate that. This is actually to then connect to non-experimental studies. This has not caught on, I don't think. But this is actually one reason why I've actually often thought that instead of using like effect sizes from small pilot randomized trials to inform power calculations, maybe we should rely on large non-experimental studies as informative for interventions that already exist or that we might have data on. Maybe we're better off getting effect size estimates from a non-randomized setting and using that to power a subsequent trial versus relying on like a small pilot. So again, in the spirit of just throwing out crazy provocative ideas, I'll leave it there.
Awesome. Well, thanks, everyone. Dr. Eisenhower, I hand the conch back to you.
Sorry, what did you say?
I hand the contract to you,
Okay, sure.
One of the Flies reference, sorry.
Yeah, if anyone else has questions, feel free to ask. I have a question that it's kind of a follow-up to that, so I can ask that, which is I'm very interested in the role of the statistician in a team. And so power analysis is one of the first opportunities that statisticians get to be part of the team, the study team. And so I'm curious, in all of your experiences, if you have advice for that role, how to kind of set the tone for what your role is going to be on the project the rest of the time. You're in the very beginning of the design phase, and then you might, they might like kick you out for part of it, and then you might come back later, just kind of navigating that environment.
I'll jump in there. I love that question as a way to prompt us how to think about that. Like I hadn't made the connection before, but yes, certainly I think all of us as statisticians have been in these scenarios where someone is like, I'm submitting a grant in 2 days. Can you do a quick power calculation for me? And of course, that is not what any of us hope is going to happen. And so it's true, answer one in that case is no, I don't have time. But I think a more complete conversation there, it's a great point. Like that could be an opportunity to sort of dig into like some of the complications that may end up coming up later. Like, yeah, I can do some power calculations, but here's what we have to think about. And here's, how do we think about these complications? Are you interested in moderation? Cue that. Or is it cluster randomized? Is it individual? So it's true. That's a nice positive spin on those outreaches that are the like, can you just do a power calculation for me? And maybe we can sort of use those to help make the whole study better by sort of opening that conversation, because it is true. probably a power calculation is going to be needed in whatever proposal, and sort of thinking through how to then make that turn into the deeper collaboration, I think is a great idea.
I was going to say something, I think that's sort of similar, which is I have kind of given up. So if I think about it as the project that they've asked me about, it usually just makes me frustrated, right? Because in that case, I feel a little bit like I'm being asked to do something that it feels almost dishonest, like they're, they know the sample size that they can budget for. And now I'm supposed to like figure out how to rationalize what that sample size is, right? So you're asking me this question that is not really like, this is like a game we're playing. It feels like, but if I've kind of convinced myself in some of these situations that you have to think of it as the relationship with the researcher, not this particular project. And that if you can develop this relationship with this team, that maybe this first project or this proposal is, you're not able to influence it because it's due tomorrow, but you begin a relationship with them that you can, now you get to work with them over time, and over time you get to start, you get to talk to them more and have more conversations where you get to fundamentally change the way they think about how they do their research. And I've had that. I mean, I should say I've had relationships like that. So I had a group that I worked with at one point earlier in my career that had come to me with, they were wanting to do factorial designs. Essentially, they were wanting to have 2x2 experiments with 20 schools total. So 5 schools in each group. And I like nearly spit out my water, like that, you can't do that, right? And they were already they were like, we already got funding to do this, right? And so, like I had to like help figure out what they could possibly do. But then over, time, you could educate this group on what was actually feasible or not feasible. I ended up training a lot of their students. They took classes, like, it became an opportunity for, a whole research group to actually learn a lot about methods as an entry point. So a place where I could have just said like, no, I'm better than you, like I know this thing and you guys don't, became an opportunity, I think. And I guess that I have to balance that myself sometimes as a statistician, I think is reminding myself that like I have expertise that other people don't, and that sometimes people sincerely don't know something that I do, and how to use opportunities to like actually weasel your way in to make science better.
Yes, as the non-statistician in the group, that's exactly what people like me want in our statisticians, is this kind of partnership to help us think about these issues that we might not understand. And also, I think in my experience, some of the things that have been helpful is like your statistician has kind of substantive knowledge of the subject matter. So like getting a biostatistician who's been working on cancer trials to come and talk to me about my, school-based behavior problems. The mechanics of doing power analysis may be the same, but all of the subtleties that we've been talking about aren't. And so having that kind of, I understand these kinds of fields of psychology or education or, crime and justice or whatever is really helpful. And then you partner instead of calling your statistician the day before. So I learned that one in graduate school.
Thank you so much. That was great.
I would just add, I mean, I think that curiosity and a lot of self-deprecating humor goes a long way as a statistician. People are scared of statisticians, on teams. Like, it's easy to come in and to sound really harsh. Like 90% of what we tell people is that they're doing things wrong and that their study is too small, right? Like it is incredibly rare that I have gotten the opportunity to say like, actually, your study is overpowered. Like, how often do you say that, right? Like, most of the time you're like, actually, your standard errors are too small. Actually, you needed a bigger sample. Oh, you did this wrong. Like, we always have bad news most of the time. So I just try to make light of it a lot, that like I realize that I'm mostly the bearer of bad news. And I just try to be like very self-aware of that role. And I think it helps, honestly, like being a little self-aware of what your job is in the room, that sometimes the job of the scientist is to be very excited about what they're doing, and to be of somebody planning an evaluation is to be very excited and hopeful that it's going to work. And your job is actually to sometimes to put the brakes on, and to make it a little more robust. And so just, I don't know, I think being very self-aware of that is helpful.
Yeah, and I'll just jump in. I totally agree. And I think this is also where we as statisticians could do better to come with some solutions, or at least try to sort of open the door towards that. So not just the like, no, you shouldn't do this, but like, well, this probably won't work out well. But, and it's things like, new statistical methods and results on covariate adjustment. Like, well, your study's underpowered, but maybe there are some prognostic covariates that we can pre-specify, and that will help us gain precision and reduce variance. Or, maybe there are some other complementary data sources. Like, I think kind of engaging in that. And Sandra, I really appreciated your point about like, that's where sometimes I think the content knowledge can help, because if you, as a statistician, if you start to learn the content area, I think it's easier to sort of see where those solutions might come up. So I think we would all do well to be that sort of like, well, what you're planning isn't great, but here's some other options. And that would, I think, help everyone.
Yeah. Like I don't have the resources to create more sample, but I can help you make blocks, right? I can help you, design things to work with what you have.
Ruth, go ahead.
I thought I'd actually ask a question since everyone else is just listening, but kind of related to a lot of all these things. To what extent do you think we've almost done ourselves a disfavor by trapping ourselves into this binary yes/no kind of thing, that all answers have an exact, definite answer? So going back to the whole idea of power, that kind of idea that this is the absolute, this is the number that you should use for your study, and it's based right on that borderline of the 80%. Is there more scope for being a little bit more, well, yes. Oh, it's pestering me about the hand. So yeah, is there more scope for saying, well, okay, yes, you can have this amount at 80%, but maybe we should build in a little bit more that might just, even if you can't get the full thing for, say, testing moderation and stuff, but you might be able to get something out of that. So a little bit more flexibility. And I tend to think the more complex the design, the more you've built in all those assumptions, which some of them are really quite tenuous, shall we say. Should we be a little bit more honest that it's more of an art than a science sometimes? So we can't give you an exact answer, but also perhaps you don't need an exact answer as well.
I would totally agree. Sometimes there isn't an exact answer. And I would add too that, like, I like to remind people that things like 80% power and alphas of 0.05 are not something statisticians that's not statisticians telling them. That's a social rule that their fields have chosen, right? So I sometimes like to remind people of like which part is statistics and which part is like something that is a rule that is based in their field. Like I don't have to say 80% power. I'd be happy to say 70% power or 90% power, but I can help you optimize for whatever it is. What's going to make it in your field. So yeah, I think it is a little bit of an art, Ruth. I think being rigid is not helpful, as you're saying. Like, being rigid does not make people want to work with us.
Yeah, I totally agree. And I think this is actually where, coming from more of a non-experimental studies world, like that is like, it's always art rather than science. There's always untestable assumptions. There's always sort of choices about designs and how do we reduce confounding and, you know, all of this. And so I think that comes very naturally in some parts of statistics, and maybe like, and I think that it's probably better for more fields to kind of have that sort of approach and just, yeah, recognizing, I mean, when I teach causal inference, you know, the students often like they want the like flow chart and they want the like, if I follow this recipe, I will get the right answer. And I always have to tell them there is just as much art as science here. And it's partly learning the content knowledge that Sandra referenced. It's learning like, and just thinking through different aspects. That can be a tough message. It's harder to do the art than just following a recipe book. But I think that we need to recognize that that's the reality.
Yeah, and
I
would just
agree
add,
with what they said. Nothing new
Yeah,
to add.
yeah, I mean, power analyses, they're arguments. And if you think of them like an argument, I think that gives you more mental flexibility than to think of them as a number. Because arguments have assumptions, they have sort of theses, they have sort of like, well, if you believe this, then you'll probably believe this. And that gives you a lot more sort of, I think, mental flexibility as you think about designing these things. Because you're arguing that you have enough observations to detect what you think you're going to detect. And so,
I usually just present a whole load of power calculations that, you know, this is the number you need for 80%. However, if you only get this, you still get something else, you know, you just a range of different things. And it helps give that message that there is no fixed answer and that we had to make some assumptions in there, I think.
yeah. Yeah, exactly. And like, you know, helps you also order like the really important parts. Like you really need this covariate because if you don't have this, everything else falls apart. But if you have like, you know, 10% less sample, it's not going to make that big of a deal. Just make sure you get that covariate. And it helps you really sort of sort out the things that you really want to maintain.
It's an interesting way of putting it, as kind of helping to prioritize the design too of the study. There's a possibility there of the power analysis being able to help inform that.
Thank you, Ruth, for your question.
Does anyone else have questions in the audience? The panelists have any questions for anyone else?
I suppose
this has been great.
Yeah. Yeah. I mean, it's diving into the details. And so a power analysis is a great way to start your collaboration with the developers. It's a great way to really sort of test a lot of the assumptions. It's a really nice sort of oil change where you can test the tires, test the fluids, really kind of go through all the parts of the study and really make sure things line up. It's a good checkup point. So I think that's our message, or one of our messages.
Great way to end. Well, thank you to all of our speakers. This has been a wonderful session. And thank you to everyone who joined.